In elementary geometry, a polyhedron is a solid in 3 dimensions with flat polygonal faces, straight edges and sharp corners or vertices. The word polyhedron comes from the classical Greek pi omicron lambda epsilon delta rho omicron nu, as poly plus hedron. Cubes and pyramids are examples of polyhedra. A polyhedron is said to be convex if its surface does not intersect itself and the line segment joining any 2 points of the polyhedron is contained in the interior or surface. A polyhedron is a 3-dimensional example of the more general polytope in any number of dimensions. Basis for definition. In elementary geometry, the faces are polygons, regions of planes, meeting in pairs along their edges which are straight line segments, and with the edges meeting in vertex points. Treating a polyhedron as a solid bounded by flat faces and straight edges is not very precise. For example, it is difficult to reconcile with star polyhedra. Grunbaum observed the original sin in the theory of polyhedra goes back to Euclid, and through Kepler, Poinsot, Cauchy and many others. In that, at each stage, the writers failed to define what are the polyhedra. Many definitions of polyhedron have been given within particular contexts, some more rigorous than others. For example, definitions based on the idea of a bounding surface rather than a solid are common. However, such definitions are not always compatible in other mathematical contexts. One modern approach treats a geometric polyhedron as an injection into real space, a realization of some abstract polyhedron. Any such polyhedron can be built up from different kinds of element or entity, each associated with a different number of dimensions. 3 dimensions. The interior is the volume bounded by the faces. It might or might not be realized as a solid body. 2 dimensions. A face is a polygon bounded by a circuit of edges, and usually also realizes the flat region inside the boundary. These polygonal faces together make up the polyhedral surface. 1 dimension. An edge joins one vertex to another and one face to another, and is usually a line segment. The edges together make up the polyhedral skeleton. 0 dimensions. A vertex is a corner point. Different approaches and definitions may require different realizations. Sometimes the interior volume is considered to be part of the polyhedron, sometimes only the surface is considered, and occasionally only the skeleton of edges or even just the set of vertices. In such elementary geometric and set-based definitions, a polyhedron is typically understood as a 3-dimensional example of the more general polytope in any number of dimensions. For example, a polygon has a 2-dimensional body and no faces, while a 4 polytope has a 4-dimensional body and an additional set of 3-dimensional cells. In other mathematical disciplines, the term polyhedron may be used to refer to a variety of specialized constructs, some geometric and others purely algebraic or abstract. In such contexts, definition of the term polyhedron may not be consistent with a polytope but rather in contrast to it. Characteristics. Polyhedral surface. A defining characteristic of almost all kinds of polyhedra is that just 2 faces join along any common edge. Likewise, any edge meets just 2 vertices, one at each end. These 2 characteristics are dual to each other and they ensure that the polyhedral surface is continuously connected and does not end abruptly or split off in different directions. For similar reasons, the surface may not be divisible into 2 parts such that each part is a valid polyhedron. This rules out both self-intersecting compound polyhedra or figures joined only by a vertex or an edge, such as 2 tetrahedra joined at a common apex. Every simple polyhedron has at least 2 faces with the same number of edges. Number of faces. Polyhedra may be classified and are often named according to the number of faces. The naming system is based on classical Greek, for example tetrahedron, pentahedron, hexahedron, triicontohedron, and so on. Topological characteristics. The topological class of a polyhedron is defined by its Euler characteristic and orientability. From this perspective, any polyhedral surface may be classed as certain kind of topological manifold. For example, the surface of a convex or indeed any simply connected polyhedron is a topological sphere. Euler characteristic. The Euler characteristic chi relates the number of vertices V, edges E, and faces F of a polyhedron. This is equal to the topological Euler characteristic of its surface. For a convex polyhedron or more generally any simply connected polyhedron, chi equals 2. For more complicated shapes, the Euler characteristic relates to the number of toroidal holes, handles or crosscaps in the surface and will be less than 2. Leonhard Euler's discovery of the characteristic which bears his name marked the beginning of the modern discipline of topology. Orientability. Some polyhedra have two distinct sides to their surface. For example, the inside and outside of a convex polyhedron paper model can each be given a different color. We say that the figure is orientable. Some non-convex orientable polyhedra have regions turned inside out, so that both colors appear on the outside in different places. But for some polyhedra, such as the tetrahemahexahedron, this is not possible, and the surface is said to be one-sided. Such a polyhedron is non-orientable. All polyhedra with odd-numbered Euler characteristic chi are non-orientable. A given figure with even chi less than a second of may or may not be orientable. For example, the one-hole toroid and the Klein bottle both have chi equals 0, with the first being orientable and the other not. Duality. For every polyhedron there exists a dual polyhedron having faces in place of the original's vertices and vice versa, the same number of edges, the same Euler characteristic and orientability. The dual of a convex polyhedron and of many other polyhedra can be obtained by the process of polar reciprocation. Dual polyhedra exist in pairs. The dual of a dual is just the original polyhedron again. Some polyhedra are self-dual, meaning that the dual of the polyhedron is congruent to the original polyhedron. Vertex figures. For every vertex one can define a vertex figure, which describes the local structure of the polyhedron around the vertex. Precise definitions vary, but a vertex figure can be thought of as the polygon exposed where a slice through the polyhedron cuts off a corner. If the vertex figure is a regular polygon, then the vertex itself is said to be regular. Volume. Regular polyhedra. Any regular polyhedron can be divided up into congruent pyramids, with each pyramid having a face of the polyhedron as its base and the center of the polyhedron as its apex. The height of a pyramid is equal to the inradius of the polyhedron. If the area of a face is in the inradius, then the volume of the pyramid is 1/3 of the base times the height, or, for a regular polyhedron with faces, its volume is then simply. For instance, a cube with edges of length has 6 faces, each face being a square with area. The inradius from the center of the face to the center of the cube is. Then the volume is given by the usual formula for the volume of a cube. Orientable polyhedra. The volume of any orientable polyhedron can be calculated using the divergence theorem. Consider the vector field, whose divergence is identically 1. The divergence theorem implies that the volume is equal to a surface integral of, when omega is the region enclosed by a polyhedron, since the faces of a polyhedron are planar and have piecewise constant normal vectors. This simplifies to where is the ith faces barycenter, is its normal vector, and is its area. Once the faces are decomposed in a set of non-overlapping triangles with surface normals pointing away from the volume is 1/6 of the sum over the triple products of the 9 Cartesian vertex coordinates of the triangles. Since it may be difficult to enumerate the faces, volume computation may be challenging, and hence there exist specialized algorithms to determine the volume. Convex polyhedra. A polyhedron is said to be convex if its surface does not intersect itself and the line segment joining any 2 points of the polyhedron is contained in the interior or surface. A convex polyhedron is sometimes defined as a convex set of points in space, the intersection of a set of half-spaces, or the convex hull of a set of points. However, many such definitions cannot easily be extended to include self-intersecting figures such as star polyhedra. Important classes of convex polyhedra include the highly symmetrical Platonic solids, Archimedean solids and Archimedean duals or Catalan solids, and the regular-faced deltahedron Johnson solids. Convex polyhedra, and especially triangular pyramids or three simplexes, are important in many areas of mathematics, especially those relating to topology. Symmetries. Many of the most studied polyhedra are highly symmetrical. A symmetrical polyhedron can be rotated and superimposed on its original position such that its faces and so on have changed position. All the elements which can be superimposed on each other in this way are said to lie in a given symmetry orbit. For example, all the faces of a cube lie in one orbit, while all the edges lie in another. If all the elements of a given dimension, say all the faces, lie in the same orbit, the figure is said to be transitive on that orbit. For example, a cube has one kind of face, so it is face transitive, while a truncated cube has two kinds of face and is not. Such polyhedra can be distorted so that they are no longer symmetrical. But where a polyhedral name is given, such as icosahedron, the most symmetrical geometry is almost always implied, unless otherwise stated. There are several types of highly symmetric polyhedron, classified by which kind of element, faces, edges and/or vertices, belong to a single symmetry orbit. Regular if it is vertex transitive, edge transitive and face transitive. Quasi-regular if it is vertex transitive and edge transitive but not face transitive. A quasi-regular dual is face transitive and edge transitive but not vertex transitive. Semi-regular if it is vertex transitive but not edge transitive, and every face is a regular polygon. These polyhedra include the semi-regular prisms and antiprisms. A semi-regular dual is face transitive but not vertex transitive, and every vertex is regular. Uniform if it is vertex transitive and every face is a regular polygon, i.e., it is regular, quasi-regular or semi-regular. A uniform dual is face transitive and has regular vertices, but is not necessarily vertex transitive. Isogonal or vertex transitive if all vertices are the same, in the sense that for any two vertices there exists a symmetry of the polyhedron mapping the first isometrically onto the second. Isotoxal or edge transitive if all edges are in the same, in the sense that for any two edges there exists a symmetry of the polyhedron mapping the first isometrically onto the second. Isohedral or face transitive if all faces are the same, in the sense that for any two faces there exists a symmetry of the polyhedron mapping the first isometrically onto the second. Noble if it is face transitive and vertex transitive. The regular polyhedra are also noble. They are the only noble uniform polyhedra. A polyhedron can belong to the same overall symmetry group as one of higher symmetry, but will be of lower symmetry if it has several groups of elements in different symmetry orbits. For example, the truncated cube has its triangles and octagons in different orbits. Some classes of polyhedron have only a single main axis of symmetry. These include the pyramids as well as the semi-regular prisms and antiprisms. Regular polyhedra are the most highly symmetrical. Altogether there are 9 regular polyhedra. The 5 convex examples have been known since antiquity and are called the Platonic solids. These are the triangular pyramid or tetrahedron, cube, octahedron, dodecahedron and icosahedron. There are also 4 regular star polyhedra, known as the Kepler-Poinsot polyhedra after their discoverers. The dual of a regular polyhedron is also regular. Uniform polyhedra and their duals uniform polyhedra are vertex transitive and every face is a regular polygon. They may be subdivided into the regular, quasi-regular, or semi-regular, and may be convex or starry. The uniform duals have irregular faces but a face transitive, and every vertex figure is a regular polygon. A uniform polyhedron has the same symmetry orbits as its dual, with the faces and vertices simply swapped over. The duals of the convex Archimedean polyhedra are sometimes called the Catalan solids. The uniform polyhedra and their duals are traditionally classified according to their degree of symmetry, and whether they are convex or not. Pyramids. Symmetrical pyramids include some of the most time-honored and famous of all polyhedra, such as the four-sided Egyptian pyramids. Noble polyhedra. A noble polyhedron is both isohedral and isogonal, but not necessarily equal-sided. Besides the regular polyhedra, there are many other examples. The dual of a noble polyhedron is also noble. Isohedra. An isohedron is a polyhedron with symmetries acting transitively on its faces. The topology can be represented by a face configuration. All 5 Platonic solids and 13 Catalan solids are isohedra, as well as the infinite families of trapezohedra and bipyramids. Some isohedra allow geometric variations including concave and self-intersecting forms. Symmetry groups. Many of the symmetries or point groups in 3 dimensions are named after polyhedra having the associated symmetry. These include T. Chiral tetrahedral symmetry, the rotation group for a regular tetrahedron, order 12. Td. Full tetrahedral symmetry, the symmetry group for a regular tetrahedron, order 24. Th. Pyritohedral symmetry, the symmetry of a pyritohedron, order 24. O. Chiral octahedral symmetry, the rotation group of the Cuban octahedron, order 24. O. Full octahedral symmetry, the symmetry group of the Cuban octahedron, order 48. I. Chiral icosahedral symmetry, the rotation group of the icosahedron and the dodecahedron, order 60. IH. Full icosahedral symmetry, the symmetry group of the icosahedron and the dodecahedron, order 120. CNV. N-fold pyramidal symmetry. DNH. N-fold prismatic symmetry. DNV. N-fold antiprismatic symmetry. Those with chiral symmetry do not have reflection symmetry and hence have 2 enantiomorphous forms which are reflections of each other. Examples include the snub-cube octahedron and snub-icosahedron. Polyhedra with regular faces. Besides the regular and uniform polyhedra, there are some other classes which have regular faces but lower overall symmetry. Equal regular faces. Convex polyhedra, where every face is the same kind of regular polygon, may be found among 3 families. Triangles. These polyhedra are called deltahedra. There are 8 convex deltahedra, comprising 3 of the regular polyhedra and 5 non-uniform examples. Squares. The cube is the only convex example. Others can be obtained by joining cubes together, although care must be taken if coplanar faces are to be avoided. Pentagons. The regular dodecahedron is the only convex example. Polyhedra with congruent regular faces of 6 or more sides are all non-convex, because the vertex of 3 regular hexagons defines a plane. The total number of convex polyhedra with equal regular faces is thus 10, comprising the 5 Platonic solids and the 5 non-uniform deltahedra. There are infinitely many non-convex examples. Infinite sponge-like examples called infinite skew polyhedra exist in some of these families. Johnson solids. Norman Johnson sought which convex non-uniform polyhedra had regular faces, although not necessarily all alike. In 1966, he published a list of 92 such solids, gave them names and numbers, and conjectured that there were no others. Victor Zagala proved in 1969 that the list of these Johnson solids was complete. Other important families of polyhedra. Stellations and facetings. Stellation of a polyhedron is the process of extending the faces so that they meet to form a new polyhedron. It is the exact reciprocal to the process of faceting, which is the process of removing parts of a polyhedron without creating any new vertices. Zonohedra. A zonohedron is a convex polyhedron where every face is a polygon with inversion symmetry or, equivalently, symmetry under rotations through 180 degrees. Toroidal polyhedra. A toroidal polyhedron is a polyhedron with an Euler characteristic of 0 or smaller, equivalent to a genus of 1 or greater, representing a torus surface having one or more holes through the middle. Space-filling polyhedra. A space-filling polyhedron packs with copies of itself to fill space. Such a close packing or space-filling is often called a tessellation of space or a honeycomb. Some honeycombs involve more than one kind of polyhedron. Compounds. A polyhedral compound is made of two or more polyhedra sharing a common center. Symmetrical compounds often share the same vertices as other well-known polyhedra and may often also be formed by stellation. Some are listed in the list of Wen-Inge polyhedron models. Orthogonal polyhedra. An orthogonal polyhedron is one all of whose faces meet at right angles, and all of whose edges are parallel to axes of a Cartesian coordinate system. Aside from a rectangular box, orthogonal polyhedra are non-convex. They are the 3D analogues of 2D orthogonal polygons, also known as rectilinear polygons. Orthogonal polyhedra are used in computational geometry, where their constrained structure has enabled advances on problems unsolved for arbitrary polyhedra, for example, unfolding the surface of a polyhedron to a polygonal net.